I did. It's down there. Cool. I got. Okay, back to work.
Wait, I need to take notes.
In the previous period's recording, they had asked some questions about rotation. And so I strongly encourage you, if you have questions about rotation, to go take a look at that recording, and hopefully that will clear up some of your questions about it. And the reason I want to not do those same questions again this time is I want to get a little bit more material in on the torque. Okay? So we're going to think of torque is that which causes angular acceleration. That which causes angular acceleration. It's by analogy to forces. You remember that for Newton's second law, we had the net force, or the sum of forces, is equal to mass times acceleration, right? Now, in order to consider angular acceleration, what we're going to do is to consider the net torque. And so let's talk about how that's computed. With Newton's second law, we had an object, and we would have a whole bunch of forces operating on that object, right? And then we take these forces and split them into x and y components. And then we'd add up those components in the x direction, add up the components in the y direction, and we would get the sum of forces, and we would set that equal to mass times acceleration in the x and y directions, right? So we're going to do a very similar kind of a thing with torques. And here's the way that we're going to think about it. If we go back to our meter stick, we're going to consider a pivot point to be a point of rotation. And at this pivot point, where there is rotation, then we're going to consider that the object is free to rotate about that pivot without any forces acting on it. So this would be an imperfect example of a pivot point right here. You can see as the meter stick swings, it swings about this pivot point. Pivot points don't actually have to necessarily be attached to anything. So for example, if I toss the meter stick up in the air and do this, and you can see that it rotated about a point somewhere around its middle, right? And that point wasn't actually attached to anything. So the pivot point does not have to actually be attached. Then we can consider the forces acting on it. Now in our particular case, we had a 10 Newton force that was pulling straight down at the end right here. I'm oversimplifying because I recognize that there were a couple of centimeters lost on this end and a couple of centimeters lost on this end. We're going to consider those negligible.
Why is that one force going in at an angle?
At an angle? Oh, the F2 right here? Just because.
Oh, not important.
Not important. Except that when it does go at an angle like that, we had to split it into components, like x and y. And so now we're going to compute the torque about the pivot. Let's give it a name. Let's give it the name O for origin. As the product of force times distance. That is 10 newtons times 1 meter. Or 10 newton meters. That's a very good question. No, but close.
The angle makes all the difference.
So the torque about O is going to be measured as force times distance. And what torque measures for us then is the tendency to cause a rotation or an angular acceleration, really, about the pivot point. How are we doing so far? I mean, really, it's just force times distance, and there you go. But now we discover that angle actually matters here. I want to consider a slightly different scenario where we have the same pivot point O, and the same 1 meter distance, and the same 10 Newton force, except that its direction is now going to go directly into O. What kind of a tendency to cause rotation will that cause? Push with your hand directly into. Do you see any tendency to rotate whatsoever? Nor do I. In fact, all of you can do this at your table. One of you hold out your hand, and the other of you push, first of all, perpendicularly to the hand. At your table, hold out your hand. One of you hold out your hand. The other push perpendicularly to the hand, downwards, like so. Do you feel a tendency to rotate? Now push directly into the hand. Now there's no tendency to rotate. You guys are doing it funny. Here.
We're down.
Hold out your arm. There you go. Now, first of all, push straight down. Down. What? No, you push down on his hand.
Okay.
Down. Do you feel a tendency to rotate? Really? Your arm didn't rotate at all?
Oh, yeah.
Yes, and it did. Now, same thing, hold out your hand. Fist. Fist, make fist. Now push directly that way. Now there's no tendency to rotate downwards. Okay? So, what do we have here? The angle matters a whole lot. So we need to modify our formula just a little bit. The torque about O is not just force times distance,
Times the angle.
something like that. It is going to be force times the distance that is perpendicular to that force.
Whoa.
Or we can write it as the distance times the force that is perpendicular to that distance. So in the first example, the force that is perpendicular to the 1 meter distance is 10 newtons, right? In the second example, the force that is perpendicular to the 1 meter distance is 0, because that 10 newton force is pushing parallel to the 1 meter displacement. Everybody see what I'm talking about? And so in this scenario, torque is equal to force perpendicular times distance, which is 0. No tendency to cause rotation or angular acceleration. Okay then. How many of you have ever been fishing? Wow. You guys need to get outside. All right. Have you ever, or have you ever seen somebody stick their fishing pole in the sand, the end of the fishing pole in the sand, and just wait for a fish to? Oh, okay. So let's imagine that scenario here. We're going to have a fishing pole. It's going to be a 2 meter fishing pole, like so. And now we're going to have a fish pushed onto it, a 1 kilogram fish. In the class we joked it was a blockfish.
That's a fish.
And this is the point where the pole is stuck into the sand. Let's call that point A. And what I wonder is how much torque is exerted about A by the 1 kilogram mass. To make this problem complete, we need an angle. Let's give this guy a 60-degree angle like so.
It's okay, but what is the word how much to add?
How much torque?
Oh, torque.
What does it mean about?
Ah, around might be another way to say that.
Oh, like this camera, I forgot to bring my glasses, so I just zoom in.
I wonder what was going on. Nice.
So,
Okay. How much torque is exerted about A by, yes. So this phrase about A is another way of saying around the point A. So we're thinking of A right here as the pivot point, and now torque is going to be exerted around that point, causing rotation around that point.
Would it ever, like, are we ever going to do problems where, like, you know, like, if it's at this point, how much, and there's something on the end of it,
Uh-huh.
you know, let's say it's, like, off by a degree, so then it would rotate. Do we need to know how far it would go? Is that something different?
You could ask that kind of a question, and actually the answer is really easy. If it's off by a degree over here, then it will end up being off by a degree over here, neglecting friction because of conservation of energy. That makes it easy.
What about, yeah, okay, never mind.
Yep, it's a good question. All right, so we're going to do the same kind of analysis that we did for this. We're going to think of torque as force perpendicular times distance, or force times distance perpendicular. So what we need is a free body diagram. There.
Of both objects or just,
That's a great question. We're going to consider the fishing pole to be our object, and we're going to consider the blockfish in terms of the force that it exerts on that fishing pole.
10 newtons.
1 kilogram times G.
It's been a long 4 days.
And we've got our 60-degree angle. Notice that something is subtly changing about our free body diagrams. We used to not care about exactly where we put the forces, now we do. Because the force has a specific point of application that is at a particular distance from our pivot point.
Does it matter if I choose 0 to be the ground and 2 to be up at the top?
It does not matter. Good question. But what does matter is going to be the component of force that is perpendicular to this 2-meter distance, or the component of the 2-meter distance that is perpendicular to the force. And that's actually easier to compute here. Because this right here is the component of the distance that is perpendicular to the 10 Newton force. Everybody see how I'm visualizing that? And I recognize that the fishing rod doesn't actually go over and up, right? But this is, think of it as like a shadow or projection of the fishing rod in the straight down direction.
So then was it like,
Well, yeah, so
it's just a triangle, it's not a triangle, you have to find so what is it, that's, yeah, you do
Yeah.
it from.
okay, so I'll do it like this. D perpendicular over D is equal to, I'm going to think about it in terms of that angle right there, the angle between the force and the distance itself, the angle between. And since D perpendicular is opposite to that angle, and D perpendicular is equal to the sine of 30 degrees times D itself. And here now, finally, we see the difference between work and torque. Work, we were considered with the distance that was parallel to the force, right? And so we used the cosine component of that distance. Here, we're concerned with the distance that is perpendicular to the force applied, so we use the sine component.
And will this always be sine?
Yes, it will always be sine.
So wait, sine, oh, never mind.
And our force is 10 newtons, our distance is 2 meters, and the sine of 30 degrees is 0.5. So that coincidentally, we end up with a 10 newton meter torque, just like we did on the animal.
Does it matter if you put the parallel next to the F or the G? Like what's the,
You mean perpendicular?
yes,
Well, it helps keep your head straight. So we see that it's not times 2 meters, it's only times the d sine 30, which is 1 meter.
Because all the other times you were doing it other way.
Right. I was building up to this. So to summarize what we've talked about so far, the torque that we compute is going to be the component of force perpendicular to the distance times that distance, or the component of distance perpendicular to the force times that force, or, in other words, force times distance times the sine of the angle between them. And the picture that you want to draw for yourself is you've got some distance d, and you've got some random force F, and we can take that F and we can split it up into two components, F perpendicular and F parallel.
Will we ever have to do F parallel?
You already did for work computations. And it is the F perpendicular that causes the torque, so that torque about this point of rotation O is equal to force perpendicular times distance, or force times distance times the sine of the angle between. And the angle between is measured between the force and the distance right now.
And torque is like a pi symbol except without the second one.
Yeah, it's the Greek tau.
I don't like the Greeks.
The Greeks have their own problems right now.
No, just because all the different like terminology that we use from them.
It's like the Greeks copied us or something.
I'm sure that's exactly what happened. The oracle at Delphi looked ahead and saw a bin belt. How can I be more like bin belt? Then I'll make the symbols more complicated just to confuse you. All right. Now, when we had objects that had more than one force applied to them, then we computed the net force on that object as the sum of all the forces in a vector sense. When we have an object that is going to have more than one force applied to it,
It's like the average of them.
we can also compute the net torque exerted by all of those forces. So I want to consider this object right here. And it is going to have a pivot point A that is 0.3 meters from one end and 0.1 meters from the other end of the object. And this pivot point is going to have an actual pivot, like a metal pivot, drilled through it, so that the object is free to rotate about the pivot. An axle, in other words. So point A is for axle. And now on this pivot point, we're going to hang a couple of weights. And one weight is going to be a 200 Newton weight.
Why'd you put it all the way at the end?
We're going to be hanging it on the end. And the other weight is going to be a 400 Newton weight hanging at the other end. Now, we don't have to work too terribly hard to figure out how much force the axle is going to be exerting and in which direction. In order for this whole thing to not fall apart, how much force does the axle have to exert?
600 newtons up.
And 600 newtons straight up. That's exactly right.
Is that how it would possibly bend if it was like
Yeah.
something?
That's right. If you exert too much force on it, the axle will bend. Exactly it.
Or twist.
Or
Very
twist.
much. A lot.
That's right. she's alluding to something I'll come back to in just a minute. Okay? And now what we want to know is, what is the net torque about A? And so to compute this, we're going to do something very similar to what we did with forces. With forces, we took our forces, broke them up into components, and added x's and y's, right? With our torques, it's going to be similar and yet different in a couple of ways. First of all, we are not going to worry about components. We're going to let FD sine theta take care of all of those components for us, because we only have torque exerted by the perpendicular component of force and not by the parallel. That's first thing. So no x's and y's. We're just going to have one single computation. Second thing that's going to be a little bit different is that our sign convention is going to be different. With forces, we always used minuses down and pluses up, right? But here, because we're talking about rotation, we're going to use the sign convention for rotation, and that is that counterclockwise rotation is positive, and clockwise rotation is negative. And so we're going to accord to torques the sign according to whether or not they cause a clockwise or a counterclockwise rotation about point A.
Well, how would you know that until you figured it out?
Great question, and I'll show you how to visualize it. No, it's actually very easy to see. Okay, so we're going to notate our net torque just like that. This is the sum of torques about A. Please note the inclusion of the point of rotation. This is absolutely necessary, because if I considered some other point of rotation, and I could, for example, this point at the end right here, then I would get a different number. So your point of rotation determines the value that you're going to get, and you have to include that in your label. And now we're going to march down all of our forces right here, and we're going to do force times distance times sine of the angle between them. And so we'll start with our 400 Newton force. So we have a 400 Newton force times its distance from the point of application of the 400 Newtons all the way back to the pivot point. What is that distance? 0.1 meters. That's right. And now we're going to consider the sine of the angle between. But in this particular case, that's very easy. The distance is horizontal. The force is vertical. The angle between is 90 degrees. The sine of 90 degrees is 1. Is 1, which is, therefore, invisible. You can write it where you don't necessarily have to. And now we're going to consider, will this be positive torque or will it be negative torque? Remembering our convention that counterclockwise is positive, just like that.
Do we have to specify this? This is clockwise is positive and clockwise is negative?
That's the default. So no.
What's clockwise not positive?
Great question. The reason that counterclockwise is positive
Because you go from 0 to 180, 180 to...
is so that you can go this way in increasing angles around the circle.
So, is that done, do we tell time backwards?
Yeah, in some sense. Yeah.
So all the numbers should be reversed.
Yeah. And in some computer systems, 0 is here and then positive is clockwise. So then you have to do 90 minus your angle in order to get.
There needs to be a universal thing for this.
Well, it is pretty much, and it's this condition right. It's this
Well, clockwise, counterclockwise.
convention right here. All right. So now we go to the 400 Newton force, and we ask, is this rotating me clockwise or counterclockwise? And I just take and put my hand or my pen at the point A right there, and imagine rotation. Is this a clockwise rotation or a counterclockwise rotation?
Clockwise. Wait, but,
Picture a clock.
wait.
Are my numbers going up or down as I do this?
Clockwise. No, counterclockwise.
It's currently at 9 o'clock, and it's turning me towards 6 o'clock. That's counterclockwise, right?
But counterclockwise is positive.
Exactly. So that's going to give me a positive torque.
And you're not thinking about the other stuff on the sides.
Bingo. That's right. We're doing one force at a time. So I don't have to worry about any of the rest of these forces.
That's what. That's.
Now the 600 Newton force is really interesting because the 600 Newton force is exerted by the axle itself on the rod, right? And so I ask, how far away is that force's point of application from the axle? And the answer is 0. It's on the axle. And therefore, the distance is 0. It causes no rotation, no torque. It exerts no torque. In other words, an axle can never exert torque around itself.
Can we prove that? Well, can it? Like, if
Well, no,
an
the
axle.
distance is 0. Prove it.
What about twisting the axle? What does that do?
Ah, that's an interesting question. Come back to that. And then finally, our 200 Newton force. Our 200 Newton force
Is negative.
times the 0.3 meters, again times the sine of 90, which is invisible, 1. And now we put our pen right here and we say, which way is this force rotating us? It's rotating us from about 3 o'clock towards 6 o'clock in the direction of increasing numbers on the clock. That's a clockwise rotation, which is negative. So we're going to end up subtracting the 200 Newton and newtons times 0.3 meters. The key thing to pick up here are the plus and minus signs. Does everybody see how they work? Good? Good. Okay. Now, let's add them up. 400 times 0.1 is?
0.4.
Nope. 40.
40.
Move the decimal one.
I knew.
Plus 0. Minus 200 times 0.3 is? You seriously don't know how to multiply decimals?
Well, okay, wait.
Move it.
60.
Multiply by 3.
60. Right. You're going to move your decimal point 1.
Well, I said 0.4 for the first one.
Do you need explanation on it?
No.
Okay.
I'm fine. All good.
And when we add it up, we get negative 20 Newton meters. What does that mean? That means our net torque is negative. Means that this thing is going to have a tendency to rotate in a clockwise direction.
Is that because even though the heavier one's closer, the other one's farther on one?
Bingo. That's exactly
Now,
right.
what if it were, instead of 0.3, what if it were 0.2 meters then?
Then you would get 0,
There we go.
and they would balance out. That's exactly right.
So it will continually go like this until it like falls over.
Yeah.
That's something.
Now, the thing is, though, as depending upon the nature of the force, right?
Wouldn't it kind of balance out like this, though?
So if the forces are gravitational forces,
Which these are.
then, well, we don't know, actually.
You know?
I just put forces on. I didn't say what they were. But the forces are gravitational forces. They will continue to pull straight down, right?
Yeah.
So once you get to this point right here, there is no more torque being exerted.
Even if you have one on the other side?
It just one side.
Your weight would pull straight down. Both
So
pull
the other
straight
weight
down.
it would still, the weight would, it wouldn't
There's
like.
weight on both sides, but it's all in one thing, so it's like just one thing.
And you might... No, you're not going to hit a point of equilibrium.
But
until
not
you
even
get together.
gone like that, like,
Your point of equilibrium is going to be right here.
what about this though, what if we're doing this?
Still no.
But it looks like a point of equilibrium, does it not?
It's still swinging.
It's not swinging, it's because I'm not actually trying to hold it.
But it does look like a point of equilibrium, but that's because you've got it right at 50, right?
I do.
So actually, any of these would be a point of equilibrium. See? That's point of equilibrium.
Well, if you hold it a little bit off, it wouldn't go all the way.
That's point of equilibrium.
Okay,
Because
well,
that's point of equilibrium.
if I hold it like this,
But if I actually unbalance it by attaching this guy to it, okay,
and when you're still.
then this isn't going to hit equilibrium really until this This whole this guy is directly underneath.
Well, like, really, like, no,
Yeah, I mean, look at where it is. The center of mass is directly underneath my fingers.
so then isn't that, it hits equilibrium, it's equilibrium then?
Now look at the meter stick. Look at where the mass is. That force is directly underneath the finger. The rotation.
So that's just the force.
Yes, it's the force. It's not the object itself. It's how the force is. Okay? Good.
And we're done.
We should practice, see?
I like being done.
And to practice, what we're going to do is I'm going to consider a robot. Robotics is very concerned with torque.
Is this the axle?
For a simple reason, and that is that very often what we are given are motors. And what motors are able to do is to fundamentally exert torque, right? So when you hear car engines, their power is given to you in terms of torque. I say that. Power is a technical physics term, which means the rate at which energy is being delivered, which is not quite the same as torque. But the, for lack of a better term, the oomph of a motor is given in terms of its torque. Okay? Now, actually they give horsepower too, right?
Yeah,
We'll say certain
horsepower
So wait, is
not
this the
really
one-
important compared to torque. You can have a car with 3 horsepower and a hell of a lot of torque, and it's going to go faster than a car with no torque but a lot of horsepower.
I don't know that it will go fast.
Well, it would have more.
Right. It'll be able to pull heavy loads.
Okay.
Is this the one, is this an axle?
Yeah. So what we're going to have is we're going to have a motor right here.
Is the motor,
And so this motor is going to be capable of 200 ounce-inches of torque. Regrettably, in robotics, our stuff is given to us in English system, and the English system uses pounds and ounces for force, and it uses inches and feet for distance. It does. And so,
what is that, 200?
ounce-inches.
Is that a Z?
That's a Z.
What is that in metric?
Good question. So each inch is 2.5 centimeters, 2.54 centimeters, and each ounce is about 30 grams. So multiply that by,
What's a gram centimeter? Like, I don't know what the unit is to that.
and then each gram, well, it's really Newton centimeters is what we're trying to compare.
Okay.
So we would do, we can look up the numbers.
I'm just trying to figure out what do we call it, the units.
Oh, they would be Newton meters for torque. Right. That's what we've been working with. I should work out a conversion for ounce inches to Newton meters.
Let's do this.
We got time.
Let's do that after we're done with this example. Okay. So this is capable of 200 ounce-inches of torque. And now I put an arm on it, and the arm is going to be a 16-inch arm. And we're going to pretend that the arm is weightless because we're going to attach to the end of that arm 3/4 of a pound. How many ounces is 3/4 of a pound?
3/4 of a pound in ounces.
How many ounces are in a pound?
16.
16. So 3/4 of that is?
I made up a number.
It's 12.
What?
Well, I mean, seriously, 16 divided by 4 is?
I just made up a number.
16 divided by 4 is?
I can't do it.
4.
4 times 3 is? 12. All right, so we got 12.
Tired. I couldn't think of it.
Okay, so we have a 12-ounce weight here, and now we wonder, is this motor going to be capable of actually powering this 12-ounce weight through this distance? These are the kinds of computations we have to do in robotics.
Or
Right,
if we just, or you burn the motor out and it smells really bad.
Right, and you pay $3 for it, $25 anymore, right? So we want to do this computation because it takes about an hour to install everything, and maybe half an hour to install everything, including the motor and motor controller. You don't want to do that until you've done 2 minutes worth of computation to see if it's feasible. See what
Which
I'm saying?
none of our teams actually do.
No, they do. I just have to drag them through it. All right, so we're going to compute the torque at the maximum worst possible case scenario. And that's going to be when the arm is straight out. Now let's think about why that is. Well, we know gravity pulls which way?
Down.
Straight down, and therefore perpendicular to that is going to be straight across, right? So we're going to get the max torque when your arm is straight across. We'll get zero torque when it is directly overhead.
Is that why it goes, like, it goes hard,
Yeah.
really fast?
Exactly. And so if we do a free body diagram on our motor, then we would say that there is a 12-ounce force pulling straight down at a 16-inch distance. And therefore, the torque on the motor is equal to 12 inches times 16 ounces. What's 12 times 16?
Let's not ask Alexis. I only know 12 times 12 is 44.
192.
And that's ounce. Figure?
Ounce inches. And when you compare that to what the motor is capable of,
It's
it will
okay.
barely be able to do it. If you were a roboteer, would you want to do this?
No.
No, I don't think so. And here's
Make it
why.
14 inch arm.
Yeah, you want to shorten your arm, or else you want to lighten your load. One of those two things. Now, actually, there's a third thing you can do that I'll share with you in just a minute.
Move the motor up.
There's another reason that you wouldn't want to do this, even if technically the motor is capable of it, right?
It would burn it out.
It's going to put a lot of strain on it. And in addition to putting a lot of strain on it, it's also going to have an undesirable behaviors.
It goes gonna really, really slow.
It's
And
going to
then
go, she's exactly right. It's going to go really, really slowly, and then it's going to whip around like this, like that. Now, why does it do that? Because as the distance gets less and less, and as a result, the load exerts less and less torque. If that motor is exerting a constant torque of 200 ounce inches on it, then the net torque around this point is going to increase greatly as you get to here, which means that you're going to have an angular acceleration.
And then when you try to stop it, it just goes like this.
Right. Exactly. Exactly. Yeah.
You can get catapult, like, it grabs the ball and like launches it
Yeah.
into the thingy.
You
Look
do
at
it.
how catapult
That's
it
a,
goes.
It just has horrible aim. That's the only problem. All right. Now, what are the things that you can do about this?
I played Age of Empires, man.
The first thing you can do is to shorten the arm. That reduces your distance from your torque, right?
Put the motor up.
Second thing that you can do
Yeah, so
is you can lighten your load.
It's not an axle, it's a motor. But it's move the motor closer.
Well, moving the motor closer is shortening your arm. And the third thing,
Or actually shortening.
the third thing that you can do, which is what we actually do most of the time, is to employ gears. Now, I'm going to explain about gears at another time, but I'll give you the short of it right now. What gears are going to do for us is they are going to trade off
Power.
speed
For
in
power.
exchange for torque, not power. The amount of power will remain exactly the same,
Well,
because power is the rate at which energy is transferred. And if we think in terms of conservation of energy, my motor is going to transfer a certain
do
amount
you
of
actually
energy.
put the
to this.
gear onto the motor? Like you attach it with the motor head?
What you do, just so you can see it, is you put
What?
a gear onto your arm, like this, and now you put your motor off here, and you put a smaller size gear on the motor like this. We call this gearing up. So you're going from a small gear to a larger gear on the arm.
What if you went from a...
And when you do
Other way
this,
around.
then what's going to happen is we're going to end up slowing the arm down, but it's going to get twice as much torque exerted on it for half the
So it's gonna
speed,
be
or
like-
3 times as much torque for 1/3 of the speed. And that's going to not only decrease the amount of torque the motor has to exert, but it's also going to even out the speed.
wait, why is it when you upshift or you go faster?
Because the way the gears are
Is that a third one?
are labeled in the car
Are
is in
actually on.
terms of speed.
Is that a 3-to-1 gear ratio?
That's awesome.
Yeah.
You mean that 3-to-1?
Just estimating it. About,
Teachers, pardon the interruption for
About two.
an announcement.
So
NHS members have a request